Hi, this is Dana with GMAT Ninja, and today I will be talking about probability questions that might show up on the GRE exam. So, who is this video for? If you see that word probability pop up on the screen and you're instantly a little bit unhappy, then this is a good video for you. Oftentimes, we find that our students are just not that confident with probability. They just don't really know why certain formulas work or when to apply them. So, if that is you, then this is a great video for you to watch. In terms of what we will cover, we will talk about the logic behind certain probability solution paths so you can see why exactly those things work in those given situations. We'll also talk about common vocabulary that pop up in these kinds of questions, things like replacement, independent or not independent variables, mutually exclusive variables, very common words when you're dealing with probability, so we want you to know how to approach those things. And then finally, we will get a bit into some probability formulas. Again, you want to be a little careful. You don't want to just throw formulas at whatever problem that you're given. But if you can really see why the particular formula works for that question, then they can be incredibly helpful. In terms of difficulty level, we're going to start with some more basic questions and then work our way up into some more difficult questions. So even if you're aiming for that high 160s quant score, this is a good video for you. And before we dive into our first question, I just want to talk a little bit about this definition of probability. The definition is just simply it's your number of desired outcomes divided by your total possible outcomes. And just as a simple example, if you flip a fair coin, what is the probability that you end up with heads? Well, most people can see right off the bat that it's going to be half, right? 1/2. But where do these numbers come from? Well, there is one thing that would make you happy, getting a heads, right? There's only one desired outcome. And there are two things that could happen, right? Either you could get a heads or you could get a tails. So learning to divide your probability into this top and bottom can be really, really helpful for certain problems. And it's a good just overall orientation to see that word probability, and this is a definition that you've got in your back pocket. So with that in mind, we'll go ahead and do the first question. I'll throw it up on the board for a couple minutes. Take your time, work through it, and then we will talk about it on the other side. So I'll put that up now. All right, let's go ahead and talk about it. As always, if you need more time, feel free to go back to the previous screen and pause it for as long as you need. So here what we have are two different sets of numbers, and a set is just what it sounds like. It's just a list of numbers that we're working with. And we are going to choose one number from this set, one number from that set, and then when we add those two numbers together, we get x. So our question is asking whether the probability that x is greater than 9 is greater than, equal to, or smaller than the other quantity here, 1/2. So not really much we can do with this one. We will start with breaking down this probability under quantity A. And what I'm going to gravitate toward is just that definition of probability that we talked about previously. So probability is just your number of desired outcomes, right? How many ways can you achieve success? And that is divided by your total possible outcomes. For this question, I will go ahead and start with this denominator, this total possible outcomes. And what I'm asking myself here is, what could x be, right? How many different ways could I go about coming up with this number x? So the way I'm thinking about this is, well, I've got two slots, right? A slot from set S and a slot from set T. And I need to put one number in this slot and one number in that slot. So how many different numbers could I put in the first slot? Well, I've got 5 different numbers in set S, so that is my what goes in that slot. And then same thing for set T. I've got 4 options that could go there. So overall, we are left with a 5 and a 4. The question here is how to combine these numbers, right? Do I multiply? Do I add? Very common question when it comes to probability or combinatorics, which is actually what we're doing right now. And the way that I like to think about it is just to visualize what's really going on here. So we've got these 5 possibilities for S, right? And they happen to be the numbers 2, 4, 8, 9, and 10. If I choose 2 as my first number, right, my number from set S, then how many different possibilities do I have to complete my my slots here? Well, I've got 4, right? So there are kind of 4 alternate worlds that are populating off of this 2, right? But I don't necessarily have to choose 2. I could choose 4. And then what would happen there? Well, same thing, right? I've got 4 options for what number could fulfill my other slot. And then same thing for 8, and same thing for 9, etc., right? So for each of these 5 options, there are going to be 4 different possibilities that could complete my 2 slots here. Now, then how many worlds total are we left with? Well, if there are 5 options, and then from each of those 4 are springing off like that, then that tells me that I've got 5 times 4 total nodes left at the end, right? There are 20 pathways that I could end up with here. So this is not something that I would draw out on the test. This is just something to think through now so that you can kind of rehash that in your mind, but not on your paper during the test. But whenever you have this kind of branching possibilities sensation, that's when you know to multiply those numbers. So overall, our total possible numbers then, total possible values of x is 20. So that's our denominator. Looking at our numerator, we want to know the number of desired outcomes. In other words, when did we win, right? Winning means that x is greater than 9. So we're dealing with a pretty small number of numbers here, right? We've got 20 total possible, and not all of those 20 are going to be those successes. So to me, this is one where I would just count them up. You want to be careful with this. If this denominator was like 1,000, then I would not necessarily want to count up like hundreds of things and then put it over that 1,000. But here, small numbers, might as well just kind of go one by one and see, what it takes to succeed. So let's say I chose 2 as my number from set S. Is there any possible way to make this plus one of these be greater than 9? Well, the biggest number I could choose is 3, and 2 plus 3 is 5, which is well below 9. So none of those are going to work, right? So I don't have any possible way of success if I choose 2. Let's do the same thing with 4. Well, 4 and 3, when you add those up, are 7, less than 9. So again, there's no possible way with 4. With 8, we start to get into more interesting territory. If I choose 8 as that first number, my pen is dying. If I choose 8, then if I choose 0, we're not greater than 9. If I choose 1, we're at 9, but not greater, so we're not succeeding yet. If I choose a 2, though, or a 3, then we are above 9, so that is very nice. So I've got 2 possible numbers that would work with that solution. Let's say I choose 9 as my first number. Well, a 0 won't cut it, but everything else will. So I've got 3 wins with 9. And let's say that I choose 11 as my number from S. Well, that is automatically going to be greater than 9. So I have 4 ways of winning if I choose 11. So overall, counting these up, what I have are 9 desired outcomes, right? 9 ways of making it greater than 9. So my overall probability is just going to be 9 over 20. Now I'm comparing this number to that number. 9 over 20 is a little bit less than 1/2. So my final answer is going to be quantity B is bigger. And that is how you go about solving this question. So a couple of key takeaways here. One is that this setup can be really helpful, right? Just to kind of separate, okay, first I'm going to deal with my total possible, then I'm going to deal with my desired outcomes. Second is this, right? So when do you multiply these numbers? Well, if you've got that branching kind of scenario, that is when I would multiply. And then the third is when you're dealing with small numbers, maybe just kind of count them up, right? How many ways can you win? Be careful with that though, because as soon as those numbers get a little bit bigger, that is not a viable option. So that's the first question. Let's go ahead and do another. I'll pop it up on the screen. Take your time, and then we will talk about it. All right, let's go ahead and talk about this question. So we have this pub, and in the pub are 4 booths, and Charles really likes going to this pub. He's going to go 4 times in 1 month. With this scenario, what is the probability that on these 4 visits, Charles sits in each of the booths 1 time? Now, what I'm thinking about here are these 4 visits. So let's go ahead and just organize those with 4 slots. And going into that very first visit to the pub, what would make us happy, right? How many times would we win when he is sat at a booth? Well, he has not sat at any of the booths yet. This is his very first seating. So he could sit at any of the 4 booths and we would still be happy. We'd still be on our way to success. So the probability of success on that first one is 4 out of 4. So now it's the second visit, and he's already sat in 1 booth. So how many options do we have of booths that he could sit in that would lead to success? Well, there are 3 left out of our 4. And then, now that second visit is done with, we're moving on to the third visit. Same exact scenario, but now 2 have already been taken, and there are 2 left. And then same exact thing for that 4th visit. There's only 1 booth left that he has not yet sat in, so he has to sit in that 1 booth in order for us to meet our desired outcome. So now we've got these numbers, and of course the question is how to combine them. One way of thinking about this is that when you multiply fractions together, the number gets smaller. And that is what we want in this scenario, right? It gets harder and harder as time goes on will Charles be sat at the booth that will lead us to success? Well, by the end, it's a pretty low chance, right? So the chances of all of this working out really nicely are going down and down and down as he visits the pub each time. So that's what happens when you multiply fractions, right? Fraction times a fraction is going to be a smaller number. So that's one way to check that, yep, it makes sense to multiply in this scenario. Now, before we multiply, let's go ahead and make our lives easy, cancel out some of these numbers, and we are left with 3 on the top, and we are left with 4 times 2 times 4 on the bottom, which is 32. So overall, we are going with answer choice D, 3 out of 32 is the probability here. All right, let's go ahead and do another question. I'll throw it up on the board, and then we will talk it through. Okay, so here we've got a quantitative comparison, and we are given that the probability that Bob will go bowling each weekend is 0.3. And of course, this is written as a decimal. It's the exact same thing as writing as a fraction. You could change that to 3/10 if it makes you more comfortable. And then what we're trying to compare is the probability that Bob will go bowling on at least one weekend out of 3 weekends, and then comparing that to a particular number. So what pops off the page immediately to me is this language, at least one. So what does at least one mean? It means one or more. So for this particular question, we are happy if Bob goes bowling exactly once, exactly twice, or exactly 3 times. So to calculate the probability of that, you could individually calculate all of those scenarios, once, twice, 3 times, and then add them up to get your probability of any of them happening. But that's kind of a lot of calculation. Don't love it. Not my favorite way of going through this question. A different way of thinking about this, at least one, is to think about how it relates to the probability of nothing. So let me give you a different example. Let's say that you're in your hometown and you go up to a random house. What is the probability that that house either has no dogs in the house at all, or has at least one dog in the house? Well, the probability of one of those two things being true, right, has to be 100%, right? Because there is nothing else beyond those. You either have no dogs or you have at least one dog. At least one is from 1 up to 1 billion dogs, right? Or even more. So the only possible outcomes are none or at least one. That covers the entire gamut. So if you just write that out as a little formula, what you get is that the probability of none plus the probability of at least one is equal to 100%, right? Nothing else could possibly be true. Here I'm going to write it as 1. Now, for this question, what we care about is the probability of at least one. So let's go ahead and just solve this for that by subtracting the probability of none. What we're left with is the probability of Bob going bowling at least once is equal to 1 minus the probability of him not going bowling at all. Now, all we have to calculate is this, right? This probability of failure of not going bowling, and then we just subtract it from 1, right? Much, much more straightforward than trying to calculate all the ways that he could succeed and then adding them up. So what is the probability that he won't go bowling at all? Well, the probability that he will go bowling on a given weekend is 0.3. And there are only two things that could happen. Either he goes bowling or he doesn't, right? There's no overlap there. There's no other scenario that could happen. And that tells us that the probability that he does not go bowling must be 0.7, right? Because these things have to add up to our total, our 100% probability. So on a given weekend, the probability that he doesn't go bowling is 70%. So let's go ahead and think about our 3 weekends. On the first one, he would not go bowling 70% of the time, same thing on the second one, and same thing on the third one. And now, just like on the last question, to combine these, what we do is we multiply, right? It's getting less and less likely that every single time he's going to fall into this exact bucket. When you go ahead and do this, and this is where I would pull out my calculator, because why not, you end up with 0.343. So this is the probability that he will not go bowling at all. And what we want is 1 minus that. So 1 minus 0.343. Again, I would just go ahead and do this in my calculator, and you would get 0.657. So this is the probability that he will go bowling at least once during these 3 weekends. Now we're comparing this to 65 over 100. You could just rewrite this as 0.65. So which of these two numbers is bigger? It is going to be A. So big takeaway here is this concept of at least 1, right? At least 1 is going to be equal to 1 minus none. That is very, very helpful, and it can get a little fuzzy in people's heads, so I would recommend really thinking through why this works before you implement it the next time. All right, I'll go ahead and put another question on the board. Take your time, and then we will chat it through. All right, so what we have here is a game, and events A, B, C, and D are the potential outcomes of that game. And we learned that these are the only possible outcomes and that they are mutually exclusive. So what does that tell us right off the bat? Well, if these are the only things that can happen and there's no overlap, right? So they're, either A happens or B happens, there can't possibly be A and B happening at the same time, and et cetera for the rest of your options here. Then these must add up, right? When you add up the probabilities of each thing happening, they must add up to 100%, right? There's just nothing else that could possibly happen, and then there's no overlap kind of making the waters fuzzy at all. So that's kind of the first vocab thing that pops out to me is this mutually exclusive, and what it means is that they do add up to your 100%. And then the next thing that we learn is that the ratio of the probability of these different outcomes, A, B, C, and D, is 1 to 2 to 3 to 4. Let's table that for a second and look at our question. We're asked, what is the probability of either A or C happening? And then the next word that I'm focusing in on is this word or. We're happy with either of these things happening. So what we can do here is just figure out the probability of A and the probability of C. And because we're happy with either of those things happening, we're more likely, because we've got these two different options, that makes us more likely to succeed. We can just go ahead and add them together. Now, this is going to help us figure out the probability of A and the probability of C. So first thing I'm going to do is just organize myself a bit. So we've got a ratio A to B to C to D, and that is 1 to 2 to 3 to 4. The other bit that I'm going to throw in here is my total, right? So how many total parts are there within this ratio? And we have 10 total parts. So out of these 10 total parts, how many are A? Well, we've only got 1, so it's just going to be 1 out of 10. Is our probability of A. And then same thing for C, right? Out of our 10 total parts, how many are C? It is 3 out of 10. And just as we discussed earlier, because we're happy with either or of these, we can just go ahead and add them. 1/10 plus 3/10 is 4/10. Go ahead and reduce that down to 2/5, which is answer choice D, and that is the correct answer. So here we're just getting some nice vocabulary, right? This mutually exclusive means they add up to 100%, and this or means that we add those probabilities at the end because we are happy with either. Our odds of success go up because we've got these different options to succeed. Let's go ahead and do another one. I'll throw it on the board here. All right, let's talk it through. Here we're told that the probability of A or B or both events happening is 0.58, and that the probability of A happening is 0.3, and also that A and B are independent. That's a lot. So let's break it down and go one by one here. A or B or both, that both definitely stands out to me. It tells us that these things are not necessarily mutually exclusive, right? They could both happen at the same time. This word independent tells me that the outcome of A doesn't impact the outcome of B. And an easy example of things that are independent is if you are flipping two different coins, right? So let's say you're flipping two different coins and you want to get heads on both. Well, the outcome of the first flip doesn't impact at all the second flip, right? It's still going to be the same probability on that second flip, regardless of what happens on the first one. So you would get 1/2 chance of success on the first, 1/2 chance of success on the second. And then because these are independent, that's what allows you to multiply them across, right? And say that, all right, well, the chance of getting both heads is just 1 times the other. So we'll come back to that concept when it comes to this question in a second. Now, thinking about this situation with the overlap, I think it's useful to throw a Venn diagram on the board just so that we can see visually what's going on here. Here, maybe let's say this is the chances of A happening, right? And here is the chances of B happening. Let's say that I just count up all of the chances of A happening. That would encompass this whole circle, right? So to include this part outside, and then also this thing in the middle where it overlaps with B. And that is going to be my probability of A. Same thing if I count up all of the probability of B. That is going to include this bit and then also the bit in the middle, right? So if I add these up, probability of A and probability of B, then what's happening is I'm double counting this bit in the middle, right? What I really want to have happen is just to count it 1 time, right? So to understand, how much of the world fits into these 2 buckets, I would want to say, well, let's maybe count the whole circle of A, but then I've already dealt with the middle. I just need this bit of B. But unfortunately, what I've done is I've included it both times, right? So it's counted twice. So to correct for that, what we can do is just say, well, I only want to count it once, so let me just go ahead and subtract one of those times out. So the probability of something falling into these 3 areas is going to be the same as, well, if I take the whole of this one, add the whole of that one, and then subtract out the thing that I double counted. And we're told here that what that all equals up to is 0.58. Now, in its current form, this is still kind of a lot of variables flying around, but that's where this independent thing comes really important, right? So we just determined here on this coin flip one that I can multiply my probability of success on the first, probability of success on the second, and then when I multiply that, that is my probability of success on both. So same thing applies here. The probability of both is the same thing as the probability of A times the probability of B. And now we've got a nice simple equation that only has 2 things going on, right? Probability of A, probability of B, and then we subtract out the probability of both. Next thing we know is that the probability of A is 0.3, so we'll just go ahead and substitute in. So we get 0.3 plus the probability of B minus 0.3 times the probability of B is equal to 0.58. We can go ahead and simplify this a bit. This is going to be, when I combine these 2 terms, 0.7 times the probability of B. And then I will go ahead and subtract out 0.3, and I will get 0.28. And then we can just go ahead and divide both sides by 0.7. So probability of B is 0.28 divided by 0.7. And when I simplify that, I just get 0.4. So that is our final answer because we are just looking for that probability of B. And that is D on your answer key. So overall, this is what it looks like to use the formula, but you really want to make sure that it actually makes sense in the case that you're given, right? So the reason why it works here is first and foremost because we're told that these events are independent. If it doesn't tell you that, then you might be in trouble. And then the second thing is that we do have this overlapping thing going on, which tells us, we don't want to double count. You have to get rid of the thing that you have double counted. So I hope that's been helpful, and let's go ahead and do another example. All right. So here we've got a probability question with some variables involved. So let's see what we've got and go from there. We have a bag, and in this bag there are 5 white and X black counters, and then one counter is selected and replaced before a second counter is selected. So this word replaced definitely pops off the page at me. What replaced means is that my overall pool isn't changing, right? So I take one out and then I put it right back in, and then I'm in the same place that I started when I go for my second counter. We're then told that the probability that both counters selected are being white is 1/9, and then what we want to solve for is x, this number of black counters. So yes, there are variables, but guess what? This is just like any other probability question. We're just thinking about what are my odds of success on that first pull, on that second pull. So success means that we want both of these to be white. So how many desired outcomes are there? Well, there are 5 white counters in the bag. And then what are my total possible outcomes? What could happen? Well, I've got 5 white counters and X black counters. So together, I have 5 plus X total counters in my bag. And then I go ahead and I select that white one and I put it back. And the same exact thing happens with my second pull. I've got 5 white counters out of a total of 5 plus X counters in the bag. And what I'm told is that the probability of this happening is 1/9. So I can just go ahead and set that equal to 1/9. Now we're just in normal algebra land. So I've got a couple options here. I could go ahead and multiply out this quadratic and solve that way. Not too bad, but I'm also seeing that this is just the same thing as 5/5 plus x squared is equal to 1/9. And to me, it's just slightly more efficient to just take the square root of both sides. So I will do that. When I take the square root, I come up with 5/5 plus x is equal to plus or minus 1/3. The reason why I'm putting the plus and minus in is because I'm introducing that root. Here, with the question structured the way it is, it would be very strange to get 2 viable answers, but it is good practice to just get used to doing this, and we'll see what happens with our solutions as we solve this out. So we'll start with it equaling positive 1/3. When I cross multiply that, I will get that 15 is equal to 5 plus x. Go ahead and subtract 5 from both sides, and x is equal to 10. That seems to make sense. Let's try it with negative 1/3. What I get then is negative 15 is equal to 5 plus x. Go ahead and subtract 5. And I get that x is equal to negative 20. Now we live in the real physical world, so it doesn't really make any sense to have negative 20 counters in this bag. So we can go ahead and say that doesn't make any sense. My only viable solution here is that x is equal to 10. And that is answer choice D. So overall punchlines here. One, when you're dealing with variables in probability, it's just like any other question. You may just need to do some algebra with that. And then the second thing is this word replaced is very important, right? Because here it tells us that nothing changes between my first pull and my second pull. Whereas if there was if it was without replacement, right? If I'm taking that counter and keeping it in my hand, then when I go to reach in the bag next time, there's going to be 1 fewer white ones there, right? And then 1 fewer total as well. So that would change what would happen with my second attempt to pull a white thing out of the bag. All right, I hope that's been helpful. We will go ahead and do one last question. So I will pop that on the screen now. Take your time and we will talk about it. All right, bit of a interesting one here at the end, so I hope you got something out of it. Here we have a quantitative comparison question. We've got 10 people, and all of those people are either European or they are American. Right away, this screams to me, let's translate this into algebra, so we'll go ahead and do that. So my number of European folks, just going to define that as E, plus my number of Americans is equal to 10. Next, I'm told that if I choose 2 members of the group without replacement, the probability of ending up with 1 European and 1 American is greater than 8 out of 15. So a couple of things pop out to me here, right? So when I'm looking at my algebraic translation, greater than tells me we're going to be working with an inequality here. And then the other thing I'm looking at is this without replacement. So without replacement means that I pull someone out of the group, and then that person's over here, and my pool has gotten smaller. So that is very, very important language for these kinds of questions to make sure that your setup actually makes sense. So let's go ahead and continue with this setup and think about what success looks like, right? So we want to end up with 1 European, 1 American. How many ways could we make that happen? Well, on my first pull, I could end up with a European, and then on my second pull, I could end up with an American. Or it could be vice versa, right? I could have an American on my first pull and then a European on my second pull. So I'm happy with either or of those scenarios, which tells me that I can find one and then add it to the other, right? And that will give me my total possibility of success. So what's the possibility of this happening, right? So on that very first pull, we've got 10 people, we've got E Europeans. So my desired outcomes are E, my total possible outcomes are 10. And then I want my second person to be an American. So same thing, my now desired outcomes are A, whatever that is, but I've taken someone out of the pool, so my total possible now goes down to 9. And then same thing for this, to pull an American out of the group, there are A possible successes out of 10 total possible people, and then we are on to our second pull, we want a European, but now there are only 9 left. If you look at these are just the same thing written twice. You could also logically kind of get there from here, saying, well, this is going to be totally equivalent to each other. So we can go ahead and rewrite this as 2 times E times A divided by 10 times 9. So that is my probability of pulling out 1 European and 1 American from this group. And I know that that is greater than 8 out of 15. From here, I'm going to go ahead and just start simplifying. Let's go ahead and turn that into a 1, this into a 5. And then we'll multiply both sides by 5 and by 9 to cancel them out on this side. So right now I've got E times A is greater than 8 times 5 times 9 divided by 15. Let's simplify. We will be left with a 3, and then simplify here. We are left with a 3. So overall, kind of messy, but we are left with E times A is greater than 8 times 3, also known as 24. So from here, I've got a couple of options. I could go ahead and use this equation to substitute in a variable into my inequality. I don't love that. We were going to end up with a quadratic and an inequality, not my favorite place to be. Here, again, since we're dealing with such low numbers, to me it makes sense just to logic our way through a couple of options. Starting with, what if they're equivalent, right? What if we have 5 Europeans, 5 Americans? Would this hold true? Well, we get 5 times 5 greater than 24. Is that true? Yes, 25 is greater than 24, so 5 and 5 is an option, right? In other words, C could be true for this question. But we could break it still, right? It could be possible that one could become greater than the other, so we want to try to break it. What if we had 6 Europeans and 4 Americans? Is that greater than 24? No, 6 times 4 is equal to 24, so it's not greater than 24. Nope, doesn't work. And we could do more examples, but if you just think about it, right, 7 times 3 is going to be 21, we're getting smaller. 8 times 2 is going to be 16, we're getting smaller. So as we diverge from this equal number, we are getting smaller and smaller and smaller. which tells us that the only way to make this work, right, to make this greater than 24, is if they are both 5. So because we have to have 5 Europeans, 5 Americans, that tells us that our final answer here is answer choice C. All right, so this has been GRE probability. I hope that it's been helpful to you, and please leave any questions below, and see you on the next video.